So we have talked about how the bathymetry influences the wind-driven circulation. Remember that in the extreme case of a triangular cross-section, we said that the flow was downwind over the shallow parts and upwind in the deep part. And then if the cross-section departed from a triangular section and became more of a U cross-section, then you would have downwind flow at the surface and upwind flow underneath. So depending on the bathymetry, we could get either laterally sheared exchange flow produced by wind or vertically sheared exchange flow produced by wind. We also talked about the effects of bathymetry on tidal currents, and we saw how the strongest currents occur in the deepest part, and that there's a phase lag between channels and shoals, with the shoals changing earlier because the currents are weaker there, and also within one profile, the phase lag is such that the currents change earlier near the bottom than near the surface because of the effects of friction. So those are the main messages of last time. Today we're going to continue talking about bathymetric effects, and in particular the effects of bathymetry on tidal flows, but tidal residuals, that is, after we average out the tides. So the tides themselves can produce mean flows as they are modified by the bathymetry. And we'll see how they're mainly arising from nonlinear terms. So in order to study that, we're going to start with I'm going to use a paper by Leon O'Donnell in 2005. It appears here if you want to see the details of it. And they assume a momentum balance and continuity equation that look like that, where the capital U and V represent vertically average velocities. So there's no, in these results, we don't know anything in the vertical structure of the currents. We only know in the horizontal variability and how bathymetry is going to affect the tidal currents. So for that framework, we use this approximation. So notice that we have, what do we have here? We have the local acceleration, then the advective accelerations, pressure gradient, and friction, bottom friction, bottom stress. Notice that there's no baroclinic pressure gradient because we're assuming a homogeneous system. So before we see how these flows affect estuaries, we need to understand how the tidal flows are modified in bathymetry. Okay, so if we look at this term and we decompose it through a Fourier decomposition of these two terms, then we get this momentum, these two equations in the momentum balance and that continuity equation. The continuity equation doesn't change, but notice that the friction terms, by decomposing them in a Fourier decomposition, we get these two terms, where the R, we had seen what that R is that 8/3 of C sub B, where C sub B is the drag coefficient, remember? 2.5 times 10 to minus 3. And U naught is the tidal current amplitude. We had talked about this before, but the interesting part here is that through the decomposition, you get these two terms. One that's the linearized bottom friction, and then this interesting term that involves the relationship between the current and the sea level, right? U and eta. Remember, this relationship will be different whether the tide is progressive or if it's standing. If it's standing, U and eta will be 90 degrees out of phase, and if it's progressive, U and eta will be in phase. Remember that? That applies to wind waves also. So you've seen and heard about this, I think, probably several dozen times by now, in different classes. Okay, so the technique to use this system of equations is a perturbation method, and that's a fancy way of saying that we can assume the solution to be a superposition of first order, second order, and higher order contributions. So the flow U and V can be decomposed in the first order flow, which would be the tidal flow, U sub 1, V sub 1. That would be the tidal flow. That's the highest. First order means that the one with the highest variability, the strongest signal. And then the second order would be what? The average, the tidal average. So we're after the U2 and V2 here. If we know U1 and V1 from tidal, the higher order terms, U3 would be very small, so we're not concerned with that. And eta 1 would be the level variation, sea level variations due to the tide, and the eta 2 would be the residual sea level elevation, whatever is left out after you average out the tide. So if we apply that superposition to this set of equations, the momentum equations, we get the first order linearized equation. So that is, if you plug in the U1 plus U2 into each one of these, and you just bring out the terms of order 1, you get this momentum equation. What does that look like? We've seen this before. What does that momentum equation look like? The solution, you should be able to guess the solution, because we talked about it. So we have the momentum balance simply between pressure gradient, local accelerations, and friction. So we have a damped wave, right? So that's a first order solution. So that's a damped wave. The wave is being damped by friction, by bottom friction, that R that appears there. And so we can relatively easily find the U1 and V1 for this. And this is going to be important because this U1 and V1 can be used to obtain then the second order solution. How? Well, we'll see. So then if we get the second order terms of this momentum equation and tidally averaged, well, that's what the overbar means here, then we're left with this momentum equation. So notice that in most of these terms we can determine from the first order solution. So we have U1, V1, which are obtained from the solution to this momentum equation. And we have U1, eta 1 here. We don't know U2 nor eta 2. So we need to find out what U2 is. This U2 and this V2 is what the tidal residuals will be. And we'll be able to draw them in a moment. But I'm just showing you where they come from. So there's the momentum balance again for the second order solution. And then if we further define U sub t and V sub t as the transport, we're going to call them the transport velocities, as the sum of the residual flow, U2, V2, and the interaction of the flow with the sea level. This is just by definition. You can define whatever you want, and we're defining it this way here, in order so that we can determine UT and V sub t from here. So if we substitute this UT and V sub t, notice that we have U2 here and U1 eta 1, and V sub 2 V1 eta 1 here. So if we substitute that, we end up with this factor 2, because U sub t equals U2 plus U1 eta 1H. So if you put that on the left-hand side, when you move it to the right-hand side, it's going to end up with, you'll end up with only one U1 eta 1H, which is the same as here. So these equations here are essentially the same as that. And the reason I'm putting them here is because these are the transport velocity. These are the second order tidal flows, the residual flows produced by the tidal. And notice there are 3 ways in which you can produce those tidal residuals. So let's see, maybe this is the term that might look most familiar to you. So what would be that term? So you have 3 mechanisms by which you can have tidal residual flows, as given by each one of these 3 terms on those equations. So the term furthest to the right is what does that tell you? What do you think it tells you? That gradient in eta 2 should tell you something. What does it tell you? So it tells you the gradients in the residual elevation of the surface. We'll look in a minute what that means. But so that's a pressure gradient. So a pressure gradient in the residual surface elevation would produce a tidal residual flow. How about the other two terms? These terms represent the tidal stresses that we talked about before. Remember the tidal stresses. This would be the residual flows produced by lateral gradients in the flow. This would be lateral gradients, du dy. When you have strong flow in the channel, weak flow over the shoals, that produces a large du dy. That can produce a residual circulation. And this term would represent what? This u1 du1 dx. Represents the changes along the estuary. So any divergence or convergence of the tidal flow in the basin, convergence or divergence. And we don't have the W, du, dz because these are vertically integrated. Otherwise, we would have that term too. How about this term? For those of you who have studied waves, this should look something like a wave term, a second order term in your wave equations. Something that happens to the wave as it gets close to the shore, and it produces a mass flux, a net mass flux toward the beach. Remember the Stokes term, the Stokes transport. So this represents the Stokes transport. And notice is the covariance or correlation between the flow and the surface elevation. That U1 eta 1 averaged over the tidal cycle is the covariance of the flow with the surface elevation. So U1 eta 1 is the Stokes transport per unit width of beach in the case of wind waves, divided by h gives you a velocity. So that's the Stokes velocity. So the main message here, and this is what I want you to understand, is that the tidal residual velocities has three contributions. One from the Stokes mechanism, one from the tidal stress mechanism, and one from the pressure gradient mechanism. Now, this is a very neat theoretical development, but still we don't have observations yet that show each one of these terms separately. So that's a challenge for us who go out and do observations, to see if we can find a system where we can measure each one of these three contributions and see if they check with the theory that has been developed. What do they look like? Well, before we go there, notice that the Stokes and the tidal stress, that is, these two terms, and these two terms, they come from the first order tides and the tidal flows. So they all have a sub-index 1. So from the first order solution, you can derive those two terms. The most challenging term is the last one in the right-hand side, because it's a second order term. How do you determine these terms? How would you determine it? Any suggestions? Well, now I show you the continuity equation. So we need to use the continuity equation. Notice that if we solve for d eta dx or d eta dy, we have something in terms of ut and bt. So that then we can integrate and find what d eta dx is. Notice that the continuity equation here, strictly, we should have this term looking similarly to this term. But we're assuming in this solution that the bathymetry does not change in the along channel direction. So in the x direction, h, which is the bathymetry, is not changing. H is only changing across the channel. That's the assumption that we started. That I didn't mention it at the beginning, but we started with it. So dh dx is 0, so that's why you have this term expressed like that. So the conditions that we need to find d eta 2 dx is that gradient is independent of the transverse direction. In other words, the variations of the residual sea level are independent of the y direction. The sea level eta 2, the residual sea level eta 2, will only change in the x direction, but not in the y direction. Then we're going to make the conditions so that the normal flow at the boundaries at y equals 0 and at y equals b, those are the boundaries of the channel. The normal flow v sub 2 is going to be equal 0. And then we're going to use that the transport integrated across the channel, the transport of water integrated across the channel in the y direction is going to be equal to 0. So if you use those equations, those conditions, and you integrate the continuity equation, then you get an expression for d eta 2 dx, which is what you need to know the transport velocity ut vt. Again, all these terms are determined from the order 1 solution, from the tidal solution, and this d eta 2 dx is obtained from here. We assume that d eta 2 dy equals 0. So notice that d eta 2 dx depends also in this term and this term. So this term looks like what? That covariance between eta 1 and u1 should tell you what it is. So it's the Stokes transport. And the other term is the tidal stresses. So this slope, the residual slope in sea level, that is after you average out the tides, there's going to be a residual slope in sea level inside a basin. How is that possible? No, there's no wind in this solution. It is possible with wind, yes, indeed. But we're assuming no wind here. This is only produced by tides. Is it possible that tides tend to produce a slope inside a basin? Just the tides after you average out? How would that be? Friction, yes, but how? Huh? Okay, yes. So those are mechanisms that would produce a sea level slope, a residual sea level slope. So those are mechanisms. We don't know exactly how that slope would look like because it's a complicated. But just simply, if you think that the wave goes in, bounces, hits the wall, and then bounces back in, then you're going to have that the reflected wave will come back with a certain phase lag, in such a way that near the mouth where you're forcing, there's going to be less attenuation. So there's going to be a net Stokes transport in at the mouth. Right, because there's a, well, let's see if we can understand this way. We're forcing with a tidal wave at the mouth, so the Stokes drift, the tidal is progressive at the mouth. Okay, the tidal is progressive at the mouth. So U1, eta 1 are in phase. So U1, eta 1 is maximum. The Stokes drift is maximum at the mouth. Now, when you get close to the head, you have the incident and a reflected wave. So there you could have a standing wave in which U1 and eta 1 are 90 degrees out of phase, in which the Stokes drift is going to be less. So you're going to have a net Stokes drift into the basin that will accumulate in the basin. Okay, so if that's the case, so let me go back and say, so you calculate d eta 2 dx, and then you integrate it along the x to obtain what eta 2 is, the residual eta 2. And this is what Ian O'Donnell found. But notice that we have different length channels, and for a short channel, we'll see what a short channel is. A short channel where you have close to a standing wave behavior. You have a slight slope, very slight slope. Eta 2 does not change that much along the system, but for a long channel, you have this eta 2. So the eta 2 in dx becomes large for this for long channels. So the reason I show you this is because I want you to think that, to remember that the term d8 at 2 dx will produce a flow in what direction? So the mouth is at 0 and the head of the channel is at 150 kilometers. So if you have that the sea level slope, the residual sea level slope is on that, is looking like that. So notice only a few centimeters difference between the mouth and the head. So if it looks like that, d8 at dx is positive, right? But let me see if we have if we go back here to these terms up here, these are the ones that produce the net flow for the tidal residual. So if d8 at dx is positive in the solution, so ut should be negative. And it makes sense if you think that you have a slope that looks like that, the flow produced by this slope will go toward the negative direction. So the residual sea level slope in a channel, in a simplified channel that they solve, the residual slope will produce a net outflow everywhere across across the channel, everywhere across the channel and throughout along the channel. Okay, so let's look at each one of those terms, and we'll look at that slope term at the end. So, yeah, maybe I should show you the solution first, and then we'll look at the contributions of each term individually. So here's where we can see what a long channel and a short channel is. This is the cross-channel bathymetry right here. So the bathymetry looks like this. There's a deep channel in the middle and shallow areas over the sides. So now we can classify a short channel where 4 times the length of the channel divided by the length of the wave, the tidal wavelength, is less than 0.6 or 0.7. Between 0.6 and 0.7, this is the transition, 0.6, 0.7. So if the channel has a length that when you multiply times 4 and divide it by the tidal wavelength, less than 0.6 gives you less than 0.6. It means that you have a short channel. And a long channel means that you can fit 4 wavelength. You can fit 4 times the length of the channel divided by the tidal wavelength is greater than 0.6. So think of this. This would be analogous maybe to a short channel would be analogous to Panama, to St. Andrews Bay, or to Ponce de Leon Inlet, or to St. Augustine Inlet. All those would be short channels because their length, when you multiply it times 4, say the length is around 40 kilometers, times 4, it's 160. When you divide it by the wavelength of the tidal wavelength is around, I don't know, we need to how would you calculate the wavelength in those systems? Actually, let's try to do it, or an approximation. What would be the tidal wavelength in a basin depth? What's the mean depth in Ponce de Leon Inlet, for example, in that whole system, that lagoon that connects through the Ponce de Leon Inlet? What would you say the mean depth is? 5? Okay, that's probably a deep one, but let's say it's 5. So how would you calculate the wavelength? That's right. How fast does the wave travel? Square root of GH. So that's square root of 50. That's around 7 meters per second. And then the wavelength would be c times t. That is the phase speed, 7 meters per second, we said, right? Times the period, 12 hours, which is around 43,000 seconds. So 43,000 times 7, how much is that? 7 times 3, like 160 kilometers, right? So let's say around 150 kilometers. And the length of the system would be 30 kilometers. 30 might be too long, but let's say 30 kilometers. So 4 times 30, that's 120. 120 over 150. We're in the, so it would be around what? 150 over 170, right? Or something like 120 over 100. Would be around 0.7 in this. So who knows? We're near the transition, so we don't know whether it's a short channel or a long channel, just from these simple calculations. But we know that the tidal wave is almost standing, so it's closer to a short channel. So in reality, it's because the mean depth is much shallower than 5 meters, and the effective length of the system might be shorter.
Is X the length along the channel?
Yes, the length along the channel. So
maybe I didn't get the whole short channel, long channel view, but why is the short channel on the, I think that the short channel would be on the left side.
The short channel would be, in the short channel, the mouth would be either here or here or here or here. Okay, so it's a generic solution for a long channel that includes short channel here. So a very short channel, the mouth would be around here. So a channel that's only 20 kilometers long.
Okay, so the head is on the right and
the head is on the right. Okay. This is closed and this is open. Okay. Well, good question. I mean, I didn't explain this, but so that's important. So all these boundaries are closed. These are closed boundaries. This is open boundary. So the tide is being forced right here. So the mean flow, this is mean flow produced by tide. So in short channels, you should expect a net inflow in the deep part and a net outflow over the shallow part. And when you go to deep channels, to long channels, you should expect net inflow over the shallow areas and outflow in the deep part, close to the mouth of the channel. Okay. So that's a theoretical solution. Notice that there's the scale. So we're talking about very weak currents, net currents. So let's look at each one of the mechanisms that contribute to this pattern. So the first mechanism that we're drawing there is what? What mechanism is it? What does it look like? That's the Stokes, right? The Stokes mechanism. So notice that for a long channel, we have all positive values, except here that we have negative values. So it means that near the mouth, the Stokes velocity is into the channel, more strongly here over the sides, and more weakly in the deep channel. So again, here we're looking at the X, Y directions. So over the entire channel, we have net inflow practically throughout the entire channel. And the inflow here over the deepest part is weaker. And near the head of the channel, we have very weak inflow and very weak outflow. Why is the flow very weak here? Notice that it would be less than 1 millimeter per second in this area. Why would the Stokes transport essentially be zero over this area of the channel? What happens to the tidal wave in that area of the channel? Is it progressive or is it standing? Huh? So it gets to be standing. So if it's a standing wave, the covariance between the flow and the elevation is close to zero. What that means is that the flow and the sea level are 90 degrees out of phase for a standing wave. And that's why the Stokes velocities are close to zero near the head. And that's why it's strongest, the Stokes mechanism is strongest near the mouth, because that's where the tidal wave is more effective. Okay? And then, so for a short channel, notice here, if you can see the values, these values are on the order of 1 millimeter per second, and here 1 centimeter per second. So for a short channel, you have net inflow in the deep part and net outflow over the shallow parts. Very weak. Okay, so that's the Stokes drift. Then we have what is this term called? The tidal stresses. So the tidal stresses will produce what kind of tidal residual flows? Can anybody describe those patterns? They're analogous for a long and a short channel. What do you see there? They're all positive values, so that means that the tidal stress mechanism produces net inflow everywhere in the channel, and more strongly so in the deepest part, where the gradients are larger. So that's regardless of whether you have a long channel or a short channel. And also notice, for the short channel, these flows are around 5 centimeters per second. And here, the greatest values also are around 5 centimeters per second. All right, so what's the other mechanism that we're missing? The one produced by the slope. So if you remember, that should give us flows that are directed out everywhere. Is that true? It is true, right? You can see it clearly there. All negative values going out more strongly over the deepest part than over the shallow part, because R is left. All right. So, and the sum of all these three is what we saw before. Is what produces this pattern over a short channel, the pattern of net inflow in the deepest part and net outflow over the shallow part for a short channel. And for a long channel, you have that the pattern will be different depending on where you are in the channel. If you're in the long part of the channel, you're going to have net outflow over the deepest part and net inflow in the shallow part. And close to the head of the system, you're going to have weak inflow in the deep part and net outflow over the shallow part. Yes,
where
ma'am.
the velocity is around zero, is that where you have like flexuals? Do you agree with that, or
Say again?
like where the transport velocity is zero? Is that where you see a lot of the deposition of sand?
Where the transport velocity is zero. Yes, you should expect to see some effect in the sediment transport. Yeah, if there's no flow, no net flow, there should be deposition. So that's an implication of these patterns, right? So there are the resulting patterns from those three mechanisms. So this is the main idea of this whole development that we've talked about up to now. That the tidal residuals will consist of a pattern of net inflow in the channel, net outflow over the shoals, if you have a channel that's close to a standing wave or a short channel. And for a long channel close to the mouth, you're going to have the opposite pattern, net outflow in the channel, net inflow over the shoals. Remember, for the wind, we said that for the wind, we'd have downwind flow over the shallow parts and upwind flow over the deep part. That's for a triangular cross-section. So you can start thinking of how these patterns, wind and tide, would compete or would reinforce each other depending on what direction the wind is blowing and depending on whether you have a short channel or a long channel. So it starts getting complicated because you have both effects. And we're not talking about density gradients yet. We're talking about wind effects and we're talking about tidal effects. Both would produce a residual circulation. Again, these residual circulations could reinforce each other or they could compete against each other. All right? Are these patterns, theoretical patterns, observable? Do you think they're observable? Well, let's see if they're observable. And I'm going to show you a couple of examples, actually several examples of tidal residual flows. The first comes from St. Augustine Inlet, which is a short channel, and we can say that because the tidal wave is standing. The flows and sea level are close to 90 degrees out of phase with each other, so that's why we can say that it's a short channel. And the mean flow, after we measured it for a tidal cycle, looks something like that. We're looking into the estuary, into the inlet. So we're sitting here in the Atlantic Ocean looking into this lagoon. And the density gradients were rather weak during that time of measurement. This was in February of 06. And the pattern that you observe, the residual flow, the mean flow, the average after a tidal cycle consists of net inflow in the channel and net outflow over the shoals. Does that sound like what theory predicted for a short channel, right? So that's pretty encouraging. Again, this is for a system where density gradients nor wind were playing a role in the mean flows. This was mainly driven by the tidal flows. Let's look at another example. Now we go to the Baja California Peninsula here in Mexico, and then we go to the Gulf of California side, close to the southern tip. You have this bay that's called the Bay of La Paz, and then this lagoon that's called Ensenada de La Paz. You see the lagoon there? Now we're looking at results of net flows looking into the lagoon, from this bay into the lagoon we're looking. And we have examples for spring tides and for neap tides. We have depth versus distance. Notice almost 1 kilometer across. This channel that looks kind of narrow here. Can you see that channel? It's almost 1 kilometer across. So it's at least twice wider than St. Augustine Inlet, for example. So notice the bathymetry, it only goes down to 8 meters maximum. And what you have is that this is also close to a standing wave, and you have inflow in the channel and outflow over the other. I wouldn't call it shoal here because it's another channel. It's not as deep as the first one, but this is sort of consistent with what theory would predict: inflow in the deepest part and outflow over the side. This channel is quite deep and gets very close to the shore, and that's why we don't have outflow over this other side. But I'm showing this example of spring tides and neap tides because during spring tides the maximum inflow is around 9 centimeters per second, and the maximum outflow around 7 centimeters per second. Whereas in neap tides, the maximum inflow is around 5 centimeters per second, and the maximum outflow only 2 centimeters per second. So notice here the difference between spring and neap. Remember when we talked about fortnightly variability in the estuarine circulation? Remember what we talked about? We said that for neap tides, the estuarine circulation is stronger. I said it right. During neap tides, the estuarine circulation is stronger than during spring tide. And that's because there's more mixing during spring tides than during neap. Remember, that's density-driven flow. Here is tidally driven flow. So because the because this net flow is produced by tides, it's going to be stronger when the tides are stronger. So the density gradients here also were very small, not influential in this pattern. So that's why during spring tides you have stronger exchange flow than during neap tides. That's because it's driven by the tides and not by the density gradient. All right, so that's another complication to the story. Just to show you that the modulation of these net flows, I'm showing here the profile of net flows or mean flows, deep tidal flows at this channel. So you have mostly outflow in this channel, right? Outflow. And this is what this time series shows. Now we have depth versus time. Notice that we have close to 2 months of data. 60 days. And this represents, what do you think this represents, this line? Yeah, the amplitude of the velocity. So, and what does that tell you about the tides? Spring and neap tides. So you can clearly see there that this was spring, neap, spring, neap, spring, neap, spring. Neap. And the red and the yellows represent water going out. And notice that the yellows and red become more evident during what stages of the tidal month? During spring tides, right? So that's when there's more, that's what we call tidal rectification. So the tides get rectified or modified by the bathymetry and by the morphology of the system through nonlinear terms. You saw the nonlinear terms, the Stokes drift, the tidal stresses, and the sea level slope, or the residual sea level. Those are the three nonlinear mechanisms that produce these residual flows. And those are modulated by the tides. They're stronger, they're more vigorous, they feel good when it's spring tides, but they're affected by the moon. So they feel down when the moon is in quadrature with the earth and the sun. But they feel strong when they're aligned with the sun and the moon. Yeah, so maybe there's something that those people who study those things about how you feel, depending on whether it's full moon or new moon. No, nothing like that. But indeed, the currents react to that. Right? They feel strong, they feel good during spring tide. These are the tidal residuals, right? Those three mechanisms that we talked about, they feel strong. The Stokes drift feels strong. The tidal stresses feel strong. The residual slope feels strong during spring tide. They're sort of wimpy during nip tide. They feel wimpy. All right, and then the final example for short systems. Now we go to the other side of the Baja California Peninsula and on the Pacific side. And this is a lagoon that could be anywhere in the subtropical region, maybe. This is called San Quintin Bay. And I'm going to show you data from the deep part at the entrance to the lagoon. So what if I tell you that it's a standing wave, a short channel? If I told you that we had measurements in the deep part of the entrance, what should you expect to see as the mean flow? Inflow or outflow? Inflow. Let's see if that's true. That's according to theory. So here we have only 1 month of observations. And again, they're from this location right here at the entrance. And the blue means to the west and red means to the north. So it means that it's going to the northwest. Notice that it's going to the northwest all the time. These are residuals. The tides have been filtered out. Okay, so that you have the tides going in and out, but they have been filtered out. This is what's left after you filter out the tide. So notice that throughout that month of observations, there was flow going to the north-northwest, so into the lagoon all the time. More strongly when? During springtime. All right? And that's because there are no density gradients here. These net flows are produced mostly by tides, by those three mechanisms that we talked about. Okay, so that's good. We have plenty of examples of the mean flow produced by the tides in subtropical regions. Why do you think that these examples that I show you all come from approximately the same latitude? If you notice, the first example was from St. Augustine Inlet, close to 30 degrees latitude. Ensenada de La Paz is at 26 degrees north, and this one is from close to, I think it's 29 or 28 degrees north. So those are subtropical regions, right, where the freshwater inflow is rather weak. So the dominant process there could be either tides or wind. But when we're out there measuring, mostly we can measure. We cannot be out there when it's windy. So we see that although this time series would tell you when it's windy or not, but we can see that the net flow is dominated by the tides. And that, again, I insist because the density gradients are weak. Right? So these are sort of a special case of estuaries where density gradients are not relevant. Because remember what the definition of estuaries is? Does everybody remember the definition of estuary? There are 3 ingredients to have an estuary, supposedly, according to the definition given in the 1950s by Pritchard, Cameron and Pritchard. 3 ingredients. One is that that seawater is measurably diluted by freshwater runoff, that you have a semi-enclosed,
Free communication with the ocean.
and the free communication with the ocean. Very good. You were fast in finding those notes. So, according to that definition, these systems that I just showed you are not estuaries because they have very little fresh water, or rather, ocean water is not measurably diluted by fresh water. Right? But still, they are coastal bodies of water with free communication with the ocean, and they have some similarities in the dynamics to the estuary. So, I don't know if you remember if I said this, but yes, I think I did say it. That estuaries are like pornography. That it's hard to define, but you know when you see it, when you see one. So these are estuaries. Okay, so that again, I insist. This is for short estuaries. Now let's see if we have an example for a long estuary. That's more difficult to find because a long estuary might be forced by different mechanisms. But here we have the channel at the entrance to this very large inland sea in southern Chile. So we're looking at this area of the world, and we're looking at a channel that's between this island and the mainland. And although you see it as a narrow channel, it's 2 kilometers wide right there at the narrowest section. So the tide really behaves as a progressive wave, and the currents there, because the tidal range is quite large in here. The tidal range, I think, is like 10 meters right here in this embayment. So the tidal currents here typically are 3.5 meters per second. They can get up to 4 meters per second in spring tide. So we measured 3.5 meters per second when we were out there. So when we were out there, it was very hard to keep the transect, to maintain the transect. You were swept by the current. So there's a transect there in the middle of that channel. And what you see here is the mean flow. We're looking toward the ocean, sitting in the inland sea looking toward the ocean. And the dark areas represent flow going away from you into the screen, and the light areas represent flow coming toward you. So you can, with a little imagination, you can say that you have outflow in the channels and inflow in the shoal, or this shoal and over here. So this sort of not confirms, but it's consistent with the theoretical result in a long channel. Again, there are no density gradients here that affect this flow because the tidal currents are so strong that you would need a very large density gradients to compare the forcing of the tidal currents. And because of the bathymetry, you're going to have a lot of gradients. If you're out there, you actually see the eddies. What are those things that you see in the cartoons that suck you? Whirlpools. Yeah, you see whirlpools there. It's scary, actually, that you don't want to sail over them because you think they might suck you in. But as a swimmer, they probably can suck you in a good depth. But so you can actually see them. So that was very impressive. Imagine with 3 to 4 meters per second current, that is 8 knot current. With those changes in bathymetry, imagine the lateral shears that are created in the flow. Very strong shears that creates the whirlpools. And the mean flow looks something like that. Outflow in the channel, inflow over the shoals, which is the opposite to the short channel. So this is the only example that I have of long channels. Those are, like I said, those are more difficult to find. Okay, so let's take a quick break. And then after we come back, we'll talk about now the density-induced flow, how the bathymetry affects density-driven flow. How bathymetry affects. So we're going to see how bathymetry affects the density-induced flow, the estuarine circulation that we had been talking about. So in order to motivate this topic, I show you a cross-section at the entrance to Chesapeake Bay, a cross-section of the mean flow. So there's a 30-kilometer cross-section that was repeated back and forth during a full day and night. And then when you average the flows or do the least squares fit to separate the tidal influences from the non-tidal influences, the non-tidal flow looks something like that. You're looking into the estuary, and the red and yellow is water going away from you, and the blue areas is water coming toward you. So you start seeing a bathymetrically induced partition. The inflows are concentrating in the channel, and the outflows appear over the shallow parts. This is mostly density-driven flow now, in contrast to the wind-driven flow that we had been talking about, and in contrast to the tidally driven flow that we have been talking about. This is mainly driven by density gradient. So notice that instead of having the estuarine circulation that we had talked about, outflow at the surface, inflow at depth, vertically sheared, now we're talking about a horizontally sheared flow, outflow over the shoals and inflow in the channel. But that's not the case all the time or everywhere. You just go 10 kilometers further down. The transect that I showed you before is actually from approximately here. So you only go 10 kilometers seaward to this transect and you get this net flow. So if you look at in the deepest part of the channel, you have outflow in the surface and inflow at depth. So now you have a vertically sheared flow. So why is the difference, Asi? Any suggestions? The joke that the Stokes velocity feels good during springtime, but during the moon, I think is not that bad. So I don't know why it's still like that. But anyway, this has nothing to do with this, with nonlinear effects. We're talking about density-driven flow. Maybe it has to do with nonlinear effects, but we don't know yet. What do you think the difference is? Okay, so we can characterize the difference as a competition between what and what. What is this non-dimensional number? Can you tell what that non-dimensional number is? Eddy viscosity versus Coriolis and depth. So you're comparing what versus what? What oranges versus what oranges? Oranges from California versus oranges from Florida. But they're oranges versus oranges because you're comparing what versus what in the Ekman number. Yeah, you're friction versus Coriolis. So you're comparing the effects of friction versus the effects of Coriolis. And that might help you explain why you have a vertically sheared flow versus a horizontally sheared flow. So here's what we're talking about. So look at that question. Which has larger Ekman number, you think? Which has larger Ekman number? And you can imagine it from looking at the depth, the h. Notice the denominator in the Ekman number definition has an h squared. And also, if you can think of the eddy viscosity, where would you expect more mixing? Over the deepest part, over the deep cross-section, or over the shallow cross-section? So which would you say, according to that flow pattern, which would you say has a larger Ekman number? Or in other words, which has more friction, would you say? Yeah, that one. And which is the shallower one? This one or that one? This one. I think that's the right answer. No, yes, it is. that has larger Ekman number, the one above than the one below. So we can perhaps start studying this from the dynamical framework that we have seen before, plus adding another term, which I encased there in a square. Notice for the along estuary dynamics, we have been talking about, in terms of density-driven flow, we have been talking about the balance between pressure gradient, which has the sea level slope, baroclinic pressure gradient, and friction. And now we're going to add Coriolis in the along estuary dynamics. And in the cross estuary dynamics, if you remember, we have the geostrophic balance, which is the pressure gradient balanced by friction. And now we're going to add friction across. So notice that the Ekman number compares this term versus this term, or this term versus this term, or the other way around, rather. This term, because that's in the numerator, this term versus that term, and that term versus that term. So friction versus Coriolis gives you the Ekman number. And you have one set of two differential equations. These are they look like partial differential equations, but you can make them ordinary differential equations if you assume that the gradients associated with the pressure gradient, that is the slope and the horizontal density gradient, are independent of depth. So in other words, they're constant. So if they're constant, then you have a system of two equations with two unknowns, two differential equations with two unknowns. And you can solve that if you assume that the flow uv, you can put it as a complex velocity, and you can get a solution that looks something like that. It's up here. Notice that it has cosine, hyperbolic cosines. But the important part here is that the flow depends on the n, which will be the sea level slope, d eta dx, or in d eta dy. It's a complex quantity. This is the density gradient. And it also depends on this alpha that appears here, and in the hyperbolic cosines, and it also appears here, the alpha. The alpha is a measurement of how deep the water column is. It's the inverse of the Ekman layer depth. The Ekman layer depth is the square root of twice the eddy viscosity divided by the Coriolis parameter. So in other words, you can plug this in MATLAB, use this relationship in MATLAB, and prescribe a density gradient, a sea level slope, and an alpha, or in other words, an eddy viscosity for any given latitude. And you're going to get a distribution of the flow as a function of depth, where is depth, as a function of depth, z, and as a function of y across the basin, where the functionality in y is given by the depth. So h is a function of y here. So you can prescribe any bathymetry, h as a function of y in that solution. Prescribe a density gradient, a sea level slope, and eddy viscosity, and you get the solution. Now there's a problem here. And we identified a problem with defining sea level slope and density gradients independently when we talked about the solution, the algebraic solution where we started everything. When we solved pressure gradient versus friction, if you remember, we went through an algebraic, we integrated the momentum balance twice, and we arrived at a solution that depended both on the sea level slope and the density gradient. And we can't do that. We can't define those independently, because for a density gradient, a prescribed density gradient, the sea level will tilt in a certain way. It has hydrostatically consistent, right? So, for example, for a large density gradient, the sea level slope will be large, and for a weak density gradient, the sea level won't be tilting as much, right? Because light water stands taller than heavy water. So there has to be a dynamical consistency between the density gradient, d, and the sea level slope. And so you use the boundary condition that appears there. Okay. you assume that throughout the cross-section, the flow equals 0. And with that, you obtain an expression of n as a function of d, the sea level slope as a function of the density gradient. So all you need to do is prescribe a density gradient, or vice versa. You obtain an expression of the density gradient as a function of the sea level slope, and you prescribe the sea level slope. So when you do that, when you use that nice solution and put it in MATLAB, and you can play with different eddy viscosity values to obtain different Ekman numbers, and these are the solutions that you get. So what you're looking at here are density-driven flows as a function of depth and distance across the channel. We're looking into the estuary, and the white areas, the areas depicted here by white contours, represent water coming toward you out of the estuary, and dark red areas, red contours are representing water going into the estuary. So you can see, can anybody describe this exchange pattern, this flow exchange pattern? By the way, the contours are non-dimensionalized by the maximum inflow. Can anybody explain that, the exchange pattern, just qualitatively, what's going on there? You have the outflow and the inflow, right? What are they doing? You have a vertical gradient, right? So you have a vertically sheared exchange flow. And why is the strongest outflow leaning toward the right? Because of Coriolis. And also the strongest inflow is leaning toward the left, right? So this is a solution where the Ekman number is large or small? What do you think? Small, because if you look at the ratio, it means that rotation is dominating over friction. So this is practically a geostrophic exchange. There's no friction. Remember, we've looked at, we've added dynamical terms to our equations to make them the same along the estuary and across the estuary. So this would be a nearly geostrophic exchange flow with a low Ekman number. As friction starts to increase, the Ekman number increases, and notice what happens here. The inflow starts protruding higher up in the water column, and then the outflow gets separated into two branches. This branch is stronger because of Coriolis, but again, the outflow starts getting separated into two branches. So in addition to getting a vertically sheared flow, you start getting also a horizontally sheared flow. Right? So this would be an intermediate Ekman number. And a lot of estuaries, many estuaries would fall sort of in this category. And then when friction dominates over Coriolis, or it gets larger than Coriolis, you have a frictionally driven exchange flow. Still, Coriolis is causing this inflow to be asymmetrically tilting to the right. You see that? The inflow is not symmetric. And also the outflow, the right branch of the outflow is stronger than the left branch of the outflow. But now, effectively, we have two branches of outflow separated. So we have rather here a horizontally sheared flow rather than a vertically sheared flow. And that's when friction starts dominating over Coriolis. When Coriolis is not important anymore and friction dominates the exchange flow, which is the bottom panel, you have a horizontally sheared flow and not a vertically sheared flow, with two branches of outflow over the shallow parts and the inflow occupying the entire water column. So if you remember that in the Chesapeake Bay, for the deeper case, the one that you said had the lower Ekman number, looked something like this, if you remember. Let's go back. It looks something like that. And then this case would look something like this, or even like that, but more like that. Right? So that's for the along estuary flow. Then for the across estuary flow, In the case, when we had the other dynamical framework, the lateral momentum balance that is given by geostrophy implies that there are no cross-channel flows. There's no V flow. Let me show you that. If we go back here to the, if you block out in the lateral, in the across estuary momentum balance, if you block out this frictional term, there's no V flow here. And if the along estuary dynamics is between pressure gradient and friction, if you block this out, there's no V flow. So there are no lateral flows under that framework. So now we have effectively added cross-channel flows with this modification of the original framework, dynamical framework that we had established. So now we've added cross-estuary flows. And notice here, for the case of the low Ekman number, can anybody say why the arrows are pointing in those directions? If we have a nearly geostrophic balance or a geostrophic balance, it means that the lateral flow are linked to the longitudinal flows, to the along estuary flows. They're linked to the cross-channel flows through rotation. So the lateral flows will be to the right of the along estuary flow. So at the surface, the flow will be to the right, and at depth, it will be to the left in our perspective. As friction starts increasing, notice, say here, when friction dominates, you have flow going in that direction, there, and in this direction here. So you start, Coriolis does not play a role anymore, and friction is the force that balances the pressure gradient. So it's as if you had a sideways estuary, pressure gradient balanced by friction across the estuary. So you have a slope, the surface elevation sloping like this. That's what causes the flow go in that direction, and then the heavy flow would go in that direction. So a sideways estuary, as friction starts dominating. So notice that the sense of the lateral circulation changes. Okay, but I will tell you right now that that's not the full story. I will tell you how the story continues in a minute, but this is not the entire story because we're missing what seems to be an important ingredient to the dynamics. So start thinking about what important ingredient we might be missing before we get there, because I'm going to come back and ask you to see if you're awake. Okay, so before we get there and see and discuss what important part of the dynamics might be missing from this dynamical framework, we can also say that these exchange patterns are not only dependent on the Ekman number, but also on how wide the system is. Remember we talked about the internal radius of deformation? Internal radius of deformation telling us whether the effects of rotation are appreciable or not. So if you have a narrow channel, you might not be able to see the effects of rotation. But that depends on how you define narrow. So you can do also a non-dimensional, you can use a non-dimensional number to define whether it's narrow or not. And that's a Kelvin number. The Kelvin number compares is the ratio between the width of the system, the width, and the internal radius of deformation. Notice here that in this representation we have three different Kelvin numbers, but the x-axis is non-dimensional from 0 to 1. So in this case, the Kelvin number of 4 means that you have 4 internal radius of deformation in the width of the channel. 4 internal radius of deformation fit in the width of the channel. Here you have 2 internal radius of deformations that fit in the width of the channel, and here you only have around 0.7 internal radius of deformation. So effectively this would be a wide channel and this would be a narrow channel. So you can think of this as a Gulf, maybe, the entrance, say, to the Gulf of California or the Persian Gulf, wide system, and this would be a narrow system perhaps a fjord. Narrow and deep would be a fjord. And deep means that it has a low Ekman number. So notice here, I want you to get this concept, because I think it's pretty neat. So the Kelvin number tells you how wide the system is. The larger the Kelvin number, the wider the system. And the Ekman number could tell you how deep the system is. Why do I say how deep? Because when the Ekman number is low, it means that there's a lot of friction. So it means that would be a dynamically shallow system. So low Ekman number would be a shallow system. And a large A large Ekman number would be a shallow system. And a low Ekman number would be a deep system. So we're going to see here an animation of how these patterns change as we change the Ekman number. Right here you can see how the Ekman number changes. We have a very low Ekman number, so this would be a geostrophic flow. So that's why in a wide system you have the outflow leaning toward this side and the inflow to this side. And you have the lateral flow looking like that. In an intermediate width or intermediate Kelvin number, you'd have something that looks something similar to that, but the outflow almost occupies now the entire surface layer. And in this case, in a very narrow system, you have outflow at surface and inflow at depth. But still, the lateral flows are linked to the longitudinal flows through rotation. So all these three cases are for low Ekman number and different widths. So this would be a very deep system, and this would be a shallow system dynamically. They're all deep. They're all deep because it has a low Ekman number. So each frame, what we're changing in each frame is only the width, and in this case of low Ekman numbers, we have a dynamically deep. We have dynamically deep systems. So I don't know if when I press here, you're going to not see anything. So we're going to see it up on the web. So for our Korean friends, we invite them to go and see the animation in the web site. And again, we're going to see how the only parameter that we're going to change now is the Ekman number. So it's as if we were in low frictional conditions, like here, low frictional conditions, or deep system. And as the Ekman number increases, it's going to go quickly. So that's why I'm explaining all this. As the Ekman number increases, that means that the systems will become shallower, or the mixing will increase. So notice that we have asymmetrically distributed. And what happens as the Ekman number increases, as friction increases, or as you get shallower, dynamically shallower systems, you get outflow over the shallow area. So that's regardless of how wide the system is. So when friction dominates, like that, like this, when friction dominates, it doesn't matter how wide the system is. It doesn't matter, rotation will not be important when friction dominates. You're going to have outflow over the shallow parts, inflow at depth. Does that make sense? Friction is the one that dominates here, the dynamics. So it doesn't matter how wide the system is, because the width will be, how wide the system is will be determined by the internal radius of deformation. So it not only the effects of rotation are not only determined then by the internal radius of deformation, but also by how deep the system is. So that's the Ekman number. So it's not only the internal radius of deformation, but also the Ekman number. That is how deep the system is in order to see the effects of rotation. Now, in the case of where rotation dominates, you see that the width is important, but you might say that rotation effects are not evident in the narrow channel. But they are indeed important because they're producing a lateral circulation that would not be produced otherwise if rotation effects So the point here is, if you say that rotation effects are only important because the channel is narrow, that is, the internal radius of deformation is too large for the width of the system, then that's not the full story. You have to consider how deep the system is. Because depending on how deep the system is, you might have a lateral circulation that looks like this, and that's produced by rotation. If it's a shallow system, then rotation will not be important anymore. And instead of having a vertically sheared exchange flow, you're going to have a laterally sheared exchange flow. We can see that in the next representation. Now, I'm going to say all of this again, now with fixed images. So again, we have here a collection of different Kelvin and Ekman numbers, a combination of 3 by 3. We're looking into the estuary. The white contours represent water coming towards you. The orange contours represent water going away from you. Notice that the contours are blue and the filling is orange. This was nothing to do with orange and blue. It was coincidence. So here I'm showing the definition of the Kelvin number, the width of the system versus the internal radius of deformation, and the Ekman number. So we have that each well represents different Kelvin numbers with the same Ekman number. So you have low Ekman number, intermediate Ekman number, and high Ekman number. So now let's see first here for low Ekman number, that is when rotation dominates the dynamics, there's no friction. This would be a wide system and a narrow system. So again, this would be like a gulf, a deep gulf, and a deep narrow channel like a fjord. And you have the exchange patterns appearing in like that. Now, as soon as you start adding some friction, then you get the outflow being influenced by rotation here, and the inflow also being influenced by rotation. It becomes more evident here at intermediate width, but then in a narrow system, you barely see the effects of rotation on the outflow here. So this the case of intermediate Ekman number is the one that gives you the most vigorous exchange flow. If you look at the contours, the largest values of outflow and inflow occur in this middle row. So what this is telling you is that you need some friction to have a vigorous exchange flow. The rotationally driven exchange flow will not be the most vigorous. And then when we add friction, when friction dominates the exchange flow, it doesn't matter how wide the system is. So again, this would dynamically be shallow systems with outflow over the shallow parts and inflow at depth. We'll come back to these concepts when we look at classifications of estuaries, because we can use this parameter space, the Kelvin number and the Ekman number, to classify estuaries in terms of how they exchange waters, the shape of their exchange, whether it's vertically shear or horizontally shear. All right? Now here's a missing ingredient for the dynamics that has been that is a hot topic now in the estuarine community. We're trying to see how important these effects are. So an important ingredient that we're missing from this framework that I just showed you is what?
Energy.
No, we have the bathymetry there. But thank you for saying something. So the bathymetry, if you think of the processes that take place within the tidal cycle and the bathymetry, interacting with the bathymetry. So those would cause large gradients in the flow, just like in the pure tidal flows. But now we're talking about tidal flows interacting with density-driven flows. Because of the bathymetric effect, you're going to have large gradients in the flow. So the missing ingredient is these terms, the advective terms, which are analogous to the tidal stresses terms. And it's not clear to me yet what the difference between the tidal stresses terms and these terms are. This is something that we're thinking about, but this is something that came up recently, and it's probably, if they're the same, then it means that perhaps a good review of the literature should have been taken place before this work. But anyway, here's what happens. This is from a paper in 2004 that's appearing there, and these are numerical solutions. So a full dynamical framework, and we're look at these two panels first. We're looking toward the ocean. So the white contours now represent water going away from us, and the dark contours represent water coming toward us. These are solutions without rotation. The full dynamics, but no Coriolis acceleration. And notice here that for a weakly stratified situation, this would be spring tides, you have outflow and inflow vertically sheared, and you'd have this lateral circulation that looks like that. And this arises from the fact that during flood, you have the advection of high salinity water in the channel. Right over here, you have the highest advection of salinity, or the advection of high salinity, I should say. The advection of high salinity right here, because the tidal currents are strongest right here. They're weaker here because of bottom friction. So you have, at the end of flood, you have high salinity here and low salinity here at the sites. That creates a lateral pressure gradient that drives this double circulation. Now again, these are numerical results. We've looked for this on the field, these patterns on the field, and we haven't been able to see them. But anyway, these are numerical results. And the point here is that you have this weaker exchange flow during weakly stratified flows, so spring tides, and during strongly stratified flows, which would be equivalent to neap tides, you have this strong exchange flow. Now, these authors are attributing a great contribution to this mean flow from these terms, from they call it the lateral advection of momentum here. So these nonlinear terms, which are analogous to the tidal stresses, if you look at them, because these are V and U are tidal variations of the flow, and so are W and U. But look at the pattern here. The pattern is relatively strong, causing relatively strong outflows at surface and inflows at depth. And during strongly stratified conditions, then these effect of these nonlinear effects are quite reduced. So they're more strongly influencing the flow here, which also produces stronger lateral flows during the more mixed situation than during the stratified situation. Now, these are results for a relatively narrow channel, 1 kilometer wide. So these results sort of caused a stir in the community, and people are thinking about these terms now, these nonlinear terms. So think about the framework that we have established and add these nonlinear terms with these accelerations, causing this type of acceleration. So then the flows will be modified by this. So this is something in which we're thinking about. And just to reiterate the concept, or looking at it in different ways. Now we're looking here at cross-sectional averages of the absolute value of each term in the momentum balance as it changes throughout the tidal cycle, which is the x-axis, 12 hours, or a little more than 12 hours. So maximum flood is right around here in the middle, where the broken line is maximum flood, and maximum ebb is at time zero. And again, what we have here, each one of these lines represents a cross-sectional average of the absolute value of each term. So this red line represents du dt plus the barotrop, the sea level slope, pressure gradient produced by the sea level slope. You see that? Du dt plus g d8 dx. That's what that red line is. Now the dark line represents, let's call them the tidal stresses, because I like to call them that way. You can call them whatever you want. But the tidal stresses, the dark line, and then this other line would be, what's this term? Yeah, friction, right? So again, if our dynamical framework was correct, the red line and this other line would be close to each other. But also, you look at this, the tidal stress term becomes quite large, at least during flood, or right after maximum flood. Notice that the du dx term, the advective term related to the convergence divergence of the tidal flow is relatively small, and then this is the baroclinic pressure gradient. So these are variations throughout the tidal cycle, and that's for a long channel momentum, and for the cross channel momentum we'd have something close to geostrophy. There's a pressure gradient, is this line here, and well, Coriolis, they didn't look at Coriolis, but you have pressure gradient and friction closely balancing or almost balancing, but also you have, right after maximum flood, you have these tidal stresses becoming large. Right, so notice that these two are for a weakly stratified case, and the tidal stresses are large during the weakly stratified period and not during the stratified period. Again, the tidal stresses are the thick line, the thick black line, and they're rather small in this during the stratified situation. So what's important here is that these tidal stresses are asymmetrically distributed throughout the tidal cycle. Right? They're much stronger. They appear to be much stronger during flood or right after maximum flood, and that's what caused the contribution, their contribution to the mean flow, the asymmetry during the tidal cycle. So actually, it'd be quite an interesting exercise for us in the data that we're obtaining to try to calculate this contribution. If you see, we can calculate these terms, v du dy. So in one transect, you can calculate it easily because we're measuring u and v. So you can calculate du dy multiplied times v and look at the pattern. And also, this other term for the cross-channel momentum balance, you can calculate v dv dy. It'd be much more difficult to calculate this w du dz, but with a little imagination, you could perhaps do it. So again, these are numerical results, and this got us thinking. This has, even though they're results from 2004, in the past 2 years, now people are saying, but wait a second, you're not thinking about these terms, and you should be thinking about these terms to the dynamics. So it's something that the community is hot about right now, and we need to show whether we should be hot about it or not. Here are the results when you add rotation to the numerical solution. So again, you have the outflow now is a little stronger on this side because of rotation, and the inflow is also tilting. Notice the interface is tilting because of rotation. And more evident here, the inflow is asymmetrically distributed to this area because of rotation. Interestingly also, and this is another topic that is hot at the moment, is that the lateral flows are stronger when the water column is less stratified than when it is stratified. So this is the situation when it's strongly stratified, the lateral flows are weaker, and when it's just moderately stratified, the lateral flows are stronger. Again, this is for a system with that U-shaped bathymetry, only 1 kilometer wide. The question is, how universal are these results? The lateral flows are stronger during neap tides or during spring tides. And this is an argument that I had recently with a colleague, because I see different. I have a different idea about this. I think that they might be stronger under certain circumstances. They might be stronger during spring tides. So this is something that you could also look at in your data when, well, you might not be able because we only have one experiment. But it's something to think about, whether the lateral flows are stronger under strongly stratified conditions or under weakly stratified conditions. And so I say that they're weaker, the lateral flows are weaker under weakly stratified conditions because the Ekman number is larger, which suppresses the lateral flows. The lateral flows will be stronger when the Coriolis term is larger under low Ekman conditions, that is under highly stratified conditions. So this will depend again I think on the bathymetry, on the width of the system. But again, it's a topic that's hot right now, and it needs to be resolved, and it's order one. That is, should we be looking at these terms in the dynamics or not? These nonlinear terms, because apparently they're order one, and for 40 years or so, for 50 years, we had been neglecting them, and that might have been a tough neglection. Is neglection a word? I just made it up. Okay, in addition to affecting the exchange flows, the estuarine circulation, the bathymetry can also affect stratification. As you can see in these two examples that we've seen before, we're looking at cross-sections of hydrography in the lower Chesapeake Bay. We're looking into the estuary from the Atlantic Ocean, depth versus distance. So again, this coast is this coast, and this coast of the transect is here. And we're looking at three variables: temperature in white contours, salinity in dark contours, and density anomaly in different colors. And what you see here is that, where do you see the greatest stratification? The greatest difference between surface and bottom, regardless of whether it's strongly stratified like it was here in the summer of 94 or in the fall of 94 when it was much less stratified. Where do you see the maximum stratification? You see it in the channels, right? You see stratification even here when it's mixed in the shoals, over the shoals. You see stratification in the channels. The strongest stratification is right here. And you would also see it here. There's another channel here, but at the time when we did that section, we didn't know that channel was there. Anyway, so the bathymetry also causes stratification because the channels represent the path of least resistance for the high salinity, for the dense water, for the dense fluid. The dense fluid will follow the path of least resistance, and since it's dense, it's going to go to the bottom. It will remain in the bottom, and it will intrude through the channels, and that's why it will cause larger stratification there. Okay, so up to now we've seen the separate contributions from winds, tides, and density gradients, but a big challenge that we have in studying this system is how do they interplay? Those three forcing mechanisms, how do they interplay? And it's very, very difficult to do it. We're starting to do it numerically. People are starting to look at the numerical simulations in which they add different ingredients to look at the individual contributions from wind, from density gradients, and from tides, and then from bathymetry. So if you think about it, it's quite a complicated concept. So one way of starting to approach is to compare density gradients versus wind. You can do it among different parameters, but something that has been looked at because of previous work in lakes, the effects of density gradients or stratification versus wind. And that can be examined through a non-dimensional number that is called the Wedderburn number, compares the wind stress versus the density gradient. And here I show numerical simulations of a channel with that bathymetry. We're looking across a cross-section, 10 kilometers wide and around 20 meters deep at the 18, 19 meters deep at the deepest part. And these are the net flows yellow and blue, yellow and red are water is coming toward you, and blue is water going away from you. And this is the salinity field associated with this pattern. So if you look at this exchange pattern, it looks something similar to what we saw in the analytical solution. Remember, these are numerical solutions. You have the strongest outflow here and the strongest inflow here. So there's the bias of rotation. The interface is tilting like this. So it's starting to look like the analytical solution. What kind of Ekman number would you say this would be? Is it low Ekman number or high Ekman number? If it was high Ekman number, you'd have red here, and blue intruding all the way to the surface. If it was low, completely low, you'd have red here and yellow throughout the entire surface. And the blue would be more tilted toward here, and there wouldn't be this kink in the interface. So it's some we could say probably intermediate Ekman, low to intermediate Ekman number. And in this case, the wind is blowing in the direction of the outflow, that is toward us, and it's blowing weakly. So that's why it's reinforcing the density-driven exchange flow, and it's causing some mixing at the surface. If you look at the salinity distribution here, this is probably caused by that weak mixing, this layer here, uniform layer in the upper 4 or 5 meters. So that's for a weak wind going in the same direction as the density-driven outflow. So this would be a case of a low to medium Ekman number and low Wedderburn number. If you increase the Wedderburn number here, it means that you're increasing the wind stress. And the wind stress will be overwhelming the density-driven flow. So if you increase, for this same situation, if you increase, same situation of wind blowing out of the screen, what kind of flow would you expect to have? A wind-dominated flow. What would it be? It would be something like that. So the downwind flow over the shallow parts and the upwind flow in the channel. You see that? So in this case, we get, remember these are numerical solutions that look like the analytical solution of Wynand that I showed before. And we need observations to show whether this is observable. Look at the density distribution, very low salinity water coming out here, and another branch coming out here too, associated with this outflow. So again, this interplay between density-driven flows and wind-driven flows can be examined through the Wedderburn number. What are we missing here? We're missing tide, because we have bathymetry. So that's the next step, to add tide to this. And we'll stop right there if you don't have any questions.